Just like salt and pepper, mac and cheese, Walter White and Jesse Pinkman, some things just always go together. In this unit, we'll look at sequences and series. We'll learn about all the basics, some relevant formula, and we'll learn to solve some challenging problems. Let's get into it. Before we get started with our very first definition, I'd like to point out that during these videos, certain times you'll see this icon right up here in the top of the screen. That's an indication for you that this is an important idea, maybe a definition or an example that you'll need to refer back to at a future point. So you should jot it down into your notebook. This definition is for a sequence. A sequence is simply a function with a domain of natural numbers. That is to say that a sequence is an ordered list of numbers. For example, if we had a sequence of numbers that looked like this, 3, 7, 1, 18, the numbers that are actually in the sequence are the range of the function, where there's always this implied domain. What I mean is that 3 is the first term in the sequence, 7 is the second term in the sequence, 1 is the third term, 18 is the fourth term, and so on. Often, a sequence will follow a certain pattern. In our very first example here, see if you can find the missing terms in each sequence by being a good pattern detective. Pause the video and try to find the next 3 terms in each of the sequences below. And here are the answers. The first sequence, in letter A, was simply counting by 7, starting with 5. So after 26, we see 33, then 40, then 47. The second sequence is simply multiplying by 2, starting with the number 1. And therefore, after 16, we see 32 and 64, and then 128. The third sequence in letter C is simply counting the prime numbers, starting with the first prime number of 2. So after 11, we see 13, then 17, and then the next prime number is 19. And in letter D, that sequence represents the digits of pi, 3.1415926. Perhaps you can keep going. Let's look at another definition. We say that a sequence is arithmetic if it has a common difference between consecutive terms. So the sequence in letter A was indeed an arithmetic sequence. And you can see this by picking any pair of consecutive terms, say 19 and 26. If we subtract 19 from 26, we get 7. This will be true for any pair of terms that we pick in the arithmetic sequence. What that means is we can think about an arithmetic sequence more generally. We can think of the first term perhaps as a sub 1, and the second term as a sub 1 plus some number d, which is this common difference that we speak of. The third term can be a sub 1 plus 2d, exactly d more than the term that came before it, and then a sub 1 plus 3d, etc. And that means that generally speaking, I can describe the nth term of the arithmetic sequence as a sub 1 plus n minus 1d. And I see that because the very, very first term in my sequence has 0 d's, the second term in my sequence has exactly 1, the third term in my sequence has exactly 2, and the fourth term in my sequence has exactly 3 d's. So that means the nth term in the sequence will have n minus 1 d's. This is called an explicit formula. An explicit formula for an arithmetic sequence. The reason it's called an explicit formula is because it can explicitly tell you exactly what a particular term is if you know the first term and the common difference, which we know. As a quick example, say you'd like to know the 100th term in this particular arithmetic sequence. You would start by saying that you know the first term, that's 5, or a sub 1 in the formula. And then since n is 100, n minus 1 is 99, so I'll substitute that in, and I'll multiply by this common difference, which was the difference between 26 and 19, or any other pair of terms, and that is 7. And since 5 plus 99 times 7 is 698, we can be sure that the 100th term in this particular sequence would be 698. Of course, we could have found that another way. We could have simply went back to the sequence and continued listing the terms from where we left off at 47. The next term would be 7 more, and that's 54. And then after that, we'd see 61, and then 68. And we could just keep on going until we reached the 100th term in this particular sequence to find out that it was 698. And I mention that because that's another way to describe an arithmetic sequence. It's called a recursive formula. It's called recursive because the nth term in the sequence is defined based on the terms that come before it. In general, would say that a sub n, the nth term in an arithmetic sequence, is a sub n minus 1, the term that came before it, plus our common difference d. And this comes directly from our definition. In this particular instance, we would say that a sub n was equal to a sub n minus 1 plus 7. Also, given the initial condition that a sub 1 was equal to 5, that would be enough for somebody to figure out any term that they wanted in the sequence. Of course, it would be pretty inefficient, at least if you're a human. A recursive formula might be better used with a machine that could crunch the arithmetic very, very quickly. Let's take a look at an example. Given that 4k, k plus 4, and 9 minus k are consecutive terms of an arithmetic sequence, determine the value of k. We could try a guess and check method where if we thought maybe k is equal to 1, if k were equal to 1, then the terms would turn out as 4 times 1, which is 4, 1 plus 4, which is 5, and 9 minus 1, which is 8. Well, that clearly is not an arithmetic sequence because the difference between 5 and 4 is different than the difference between 8 and 5. And in an arithmetic sequence, there must be a common difference between terms. So let me ask you to pause the video again and see if you can come up with a better method besides guess and check that'll tell us the value of k. Did you find that k was equal to -1? If so, you got the right answer. But keep in mind that getting the right answer is not always all there is to solving a math problem. It's also very important that you communicate your solution as well as get the right answer. In fact, it's probably more important. Arriving at a wrong answer could be the result of a silly mistake, one that you might never make again. But failing to communicate your work and show your work is a bigger issue, and it's one thing that you'll really have to work extra hard on if you are working remotely. Of course, we should check that our answer is correct. If the value is indeed k equals -1, then when I substitute k back into the original, 4 times -1 is -4. -1 plus 4 for the next term would be +3, and 9 minus -1 would be 10. These three we can check to see if they are indeed consecutive terms of an arithmetic sequence. I can see that they are because they each increase by 7. That is to say, the common difference in this particular sequence is +7. Speaking of checking for common differences, in our third example, we're asked which of the following sequences are arithmetic. Take a second and pause the video and see if you can figure it out. But be careful, because these are not completely straightforward. You might have to think carefully about a few of them. Did you find 2 arithmetic sequences in the list? I did. Letter A is indeed arithmetic because the common difference between consecutive terms is 1/2. This is easier to see if we get a common denominator. Instead of 2/3, we think of it as 2/6, and then 5/6, and then instead of 4/3, it's 8/6, and then 11/6. So we can see that each time we're increasing by 3/6, or 1/2. Letter B is not arithmetic, and that's because the difference between root 5 and root 3 is different than the difference between root 7 and root 5. Letter C is indeed arithmetic. It doesn't seem like it is. It seems like it's almost geometric. 2, then 4, then 8, doubling all the way. But this isn't 2, 4, 8. It's the log of 2, the log of 4, and the log of 8. And so to see that letter C is indeed arithmetic, it might be good to think of 4 as 2 squared and 8 as 2 cubed. And remember that important power rule for logarithms. You can then think of this sequence as the log of 2, and then 2 times the log of 2, and then 3 times the log of 2. In case you don't remember the rule that I'm referencing, I'm saying to take the exponent of the argument and bring it down and multiply it by the log. That's helpful because then I can see that my sequence goes 1 log 2, 2 log 2, 3 log 2, the next term will be 4 log 2, and the nth term will be n log 2, which is indeed arithmetic with a common difference of log 2. Letter D, meanwhile, our last example here, is not arithmetic. The numerator is increasing according to an arithmetic sequence, and the denominator is increasing according to an arithmetic sequence. However, if you choose any 2 consecutive terms and you subtract the fractions, you will not get a common difference. In this example, we're told that the 5th term of an arithmetic sequence is 111, and the 13th term of an arithmetic sequence is 327. Pause the video and see if you could figure out the value of the first term. Did you find out that the answer for the very first term was 3? If so, you got the answer right. But as with the last example, it's important not only to try to get the answer right, but to be able to communicate your answer. There's a lot of different ways that you can communicate the work for this particular problem. I'll share one way here. Since we know that the explicit formula for an arithmetic sequence is that the nth term is equal to the first term plus n minus 1 times d, the common difference, I can write a system of equations using the given information. The first piece of information that I'm given is that the 5th term is 111. That allows me to write the equation that 111 is equal to a sub 1, which is unknown, plus 4, because that's 5 minus 1, times the common difference, which is also unknown. I can also write a second equation using the second piece of information, and that would look like this. 327 is equal to a1 plus, since it's the 13th term, and 13 minus 1 is 12, I'll say that's 12 common differences. Here is my system. If I use an elimination method, I can subtract the first equation from the second, and that will eliminate a sub 1. And that'll leave me with 216, that's 327 minus 111, is equal to 8d. Dividing by 8, and I find out that 27 is my common difference. From here, what I can do is I can plug d back into the first or the second equation, and I can figure out a. a1 is equal to, plugging into the first equation then, 111 minus 4 d's, or 4 27s, and that tells me that a1 is equal to 3. As I mentioned, there were a lot of different ways to solve this particular problem. So take a look back at your own work and compare it to mine, and see whether your work was easy to follow. If a classmate of yours were to look down and try to see what you did, or if I were grading it on a test or a quiz, would I be able to understand how you got to your answer? As I mentioned before, it's more important how you got there than whether or not the final answer you came up with was right. To push our thinking forward, we're going to need another definition. In this definition, we define a geometric sequence as a sequence with a common ratio between consecutive terms. In our very first example, you might remember this sequence. This sequence, which I've called b sub n, is a sequence of doubling. We go from 1 to 2 to 4 to 8 and so on. And this is a geometric sequence because the ratio between consecutive terms is common. It's constant. It's always 2. If I pick an arbitrary pair of consecutive terms like 16 and 32 and I divide them, 32 divided by 16, I'll get 2. And we would write that r, which is the letter often used to represent the common ratio, is equal to 2. And so, just like in the case with the arithmetic sequence, we can come up with explicit and recursive formulas to describe geometric sequences. Starting with recursive, remember that a recursive formula is one that is defined based off of the previous terms. So in the case of a geometric, we would say that b sub n is equal to r, this common ratio, this common multiplier, multiplied by b sub n minus 1. For the specific formula that we're looking at here that starts with 1 and doubles every time, we would say that b sub n is equal to 2 times b sub n minus 1. And then we also must provide the information that the first term is equal to 1 so that we know where to start. So what I have here in this box is a recursive formula that describes that specific formula of doubling beginning with 1. And a computer or something could quickly work out the 1000th term in that sequence. Of course, we aren't computers, and we might prefer to use an explicit formula, which would allow us to quickly plug a number in and work out the 1000th term or something along those lines. For an explicit formula, let's think about generalizing. So instead of starting with 1, your geometric sequence will just start with some term, b sub 1. And then the next term wouldn't necessarily be b sub 1 times 2 because the common ratio could be different than 2. But it would have to be b sub 1 multiplied by r. And then the third term would have to be b sub 1 multiplied by r and then multiplied by r again, which would be r squared. And then the fourth term would be b sub 1. So you've played this game before, and as you can now see that the nth term, according to the explicit formula, will be b sub 1, the first term, multiplied by n minus 1 copies of r. Just like we had n minus 1 copies of d added on for the arithmetic, we multiply by n minus 1 copies of r. And there is our explicit formula. So if I wanted to find the 12th term in this specific formula that I wrote right here, I would take 1, the first term in the sequence, and multiply it by 2 to the 11th. And I think most of you probably know from playing that game that 2 to the 11th is 2048. Here's an example that's similar to one that we've already done, but this time we're given that x, 3x minus 3, and 4x are consecutive terms of a geometric sequence, and you're asked to determine the value of x. Once again, pause the video and see if you can figure it out. This time, rather than subtracting consecutive terms and expecting a common difference, we'll divide consecutive terms and expect a common ratio. So 3x minus 3 divided by x should be equal to some common ratio r. Likewise, 4x divided by 3x minus 3 should also be equal to r, and thus we can skip the middleman and say that 3x minus 3 divided by x should be equal to 4x divided by 3x minus 3. Solving this proportion involves nothing more than multiplying both sides of this equation by the quantity x times 3x minus 3 in order to clear the denominators. That creates the quadratic equation 3x minus 3, the quantity squared, equal to 4x times x, also known as 4x squared. Multiplying out the binomial on the left should give you 9x squared minus 18x plus 9. And when we set that equal to 4x squared, we can regroup so that we get 5x squared minus 18x plus 9 equals 0. Solving this quadratic equation will give us our solution. Of course, there are a lot of ways to solve a quadratic equation. One way might be using the quadratic formula. Another way might be guess and checking to see if you can factor the equation. I see that 5x minus 3 multiplied by the quantity x minus 3 will do the job, which tells me that either x is equal to 3/5 or x is equal to 3. When I check these solutions, here's what I find out. If x is equal to 3/5 and I plug them back into the initial given information, I'll get the terms 3/5, comma 3 times 3/5, which is 9/5, minus 3, which is 15/5, so negative 6/5, and then 4 times 3/5, which is 12/5. When I check this one out, what I see is that this sequence, each time, it's simply multiplying by a -2 times -2 each time. And that works out. The common ratio of our geometric sequence could in fact be a -2. Meanwhile, when I plug 3 back into the original, I get that x is 3, 3 times 3 minus 3 is 6, and 4x is 4 times 3, that's 12. And we'll see that that's multiplying by a +2. Another perfectly fine common ratio. And this is a great example of why you need to make sure you show all of your work and don't rely on maybe just guessing and checking or other methods where you just sort of figure out the answer. Because as you can see here, sometimes there's more than one answer. And algebra helped us come up with a quadratic, which led to 2 legitimate answers. And our work was easy to follow. Let's take a look at another example. Here we're asked which of the following sequences are geometric. Take a second and pause the video and see if you can determine A, B, C, D, which of these have a common ratio. If you decided that they all are geometric sequences, then you can pat yourself on the back because they are. The very first one, letter A, has a common ratio of 2. And if we wanted to describe this sequence, we would say a sub n is equal to 6, the first term, multiplied by 2 to the n minus 1. The second sequence, letter B, these are under a radical, but I notice that to get from root 5 to root 10, I should multiply by root 2. And if I take root 10 and multiply by root 2, that'll give me root 20, and root 20 simplifies to 2 root 5. If I take 2 root 5 and I multiply it by root 2, I get to 2 root 10. So it is, in fact, true that b sub n is equal to root 5, that's the first term, multiplied by root 2 raised to the n minus first power. In letter C, I can see that each term is being divided by 2. Well, that's the same as multiplying by a half. So c sub n is equivalent to 200 times 1/2 to the n minus 1 power. In the last example, which is one that we'll see again, d sub n, the first term is equal to 1, and to get to the next term, we multiply by -1. That is, in fact, our common ratio, because multiplying by -1 will always alternate from +1 to -1 and back. In this example, you're asked to find the value of the common ratio given some initial terms for a geometric sequence. The 6th term is 500, and the 9th term is 4. Once again, pause the video and see if you can find the answer. You should have found that the common ratio was 1/5, or 0.2. One way to show this is through a system of equations, just like before. I know that the explicit formula for a geometric sequence is a sub n is equal to a sub 1 multiplied by the common ratio raised to the n minus 1 power. When I sub in the first piece of information, I get the equation 500 is equal to a sub 1, which is unknown, times the common ratio, which is unknown, to the 5th power, because 6 minus 1 is 5. When I sub in the second piece of information, I get that 4 is equal to a sub 1 times the common ratio to the 8th power, because 9 minus 1 is 8. Now, in order to solve this system of equations, I notice that division will allow the a1 term to cancel out. If I divide the second equation divided by the first equation, I will get the result 4 over 500 is equal to a1 r to the 8th over a1 r to the 5th. And what I notice is, well, two things. On the right-hand side of the equation, a1 divided by a1 is 1. On the left-hand side of the equation, 4 over 500 reduces to 1 out of 125. And also on the right side of the equation, r to the 8th divided by r to the 5th is r to the 8 minus 5, or r cubed. Finally, to figure out what r is equal to, say therefore, r is equal to the cube root of 1/125th, which is 1/5. At last, we've reached the second part of the duo. If sequences are the peanut butter, then series are the jelly. And a series is defined as the sum of the terms of a sequence. For example, if I started with a very simple sequence, one that began with 1 and increased by 1, 1, 2, 3, 4, you might recognize this particular sequence as the natural numbers, or the bold N that I described at the beginning of the video. The associated series, I'll use the letter S for series, would be 1 plus 2 plus 3 plus 4, and so on. And this particular series could stop after a certain point. If I wanted it to stop after 100 terms, then I could say that I want the sum of the first 100 terms and denote it just like that. 1 plus 2 plus 3, and then it would end with 98 and 99 and 100. And in fact, this is a very, very famous series, the sum of the first 100 natural numbers. As legend has it, when the mathematician Gauss was a young lad, a kindergartner, his teacher, hoping to buy a little bit of time, asked Gauss to add the first 100 numbers. And Gauss quickly responded that the sum from 1 to 100 was equal to 5,050. And Gauss knew this answer, not through some formula or through just quick arithmetic, but he knew a very important property about arithmetic sequences in general. And that is, if you were to pair the first term in the series with the last term in the series, well, in this case, 1 plus 100 would be 101. And we'd note that if you paired the second term with the second to last term, once again, you get 101, 2 plus 99. And that would also be true if you paired the third term and the third to last, and so on and so forth. So for Gauss, this was just a question of how many 101s are there? And of course, he knew that if there are 100 numbers, then there are half that many pairs of numbers, so 50 pairs. And this boiled down to just a question of doing 50 times 101, and thus 5,050 is the sum. It's very important to recognize that we can summarize Gauss's technique to find a formula that will find the sum of any arithmetic series. In fact, it's very much worth noting that anytime you can derive a formula, that is way better than memorizing a formula. And so that's what we'll do here. We will derive the formula for the sum of an arithmetic series. The formula I'm referring to is S sub n is equal to n divided by 2 multiplied by the sum of the first and the nth term of the series. This is the formula that Gauss understood that allowed him to add 1 to 100 so quickly. We're going to generalize it. What that looks like is this. Let's take a sub n, an arbitrary arithmetic series. Its first term will be a sub 1. Its second term, a sub 2. But more descriptively, we could call that a sub 1 plus d. Its third term would be a sub 1 plus 2d, and its fourth would be plus 3d. What I could do is I could say that its very last term, I'm sure its nth term, would be, according to the formula for an explicit formula for an arithmetic series, would be a sub 1 plus n minus 1 times d. And I left space here to write not just the last term, but the second to last term, and you'll see why. The second to last term will be a sub 1 plus 1 less than n minus 1d, which would be n minus 2d. Okay, so what I'm picturing here, if I'm trying to think like Gauss did, is all the numbers added from 1 to 100, but in a more general way with a sub 1s and d's. And now what I want to picture is the same sum in reverse. Instead of 1 to 100, it it would be 100 to 1. There's a good reason to set it up like this. So the last term in the series, the nth term, according to our explicit formulas there, the second to last term, I can just kind of look back over here to see what it would look like. A sub 1 plus n minus 2 times d. And then there'd be a whole bunch of terms in the middle. And then would come the second term in the series, a sub 1 plus d. And then last would come the a sub 1, the first term in the sequence. What I see now is I have a pair of equations that are both true. They're both ways of summing a generic arithmetic series, one from first term to last and the other last term to first. What I can do now is I can add those two equations together. It's a legitimate operation. On the left-hand side, when I add a sub n plus a sub n, I get 2a sub n. And what I get on the right-hand side is the really, really interesting part. So you really have to look at this. Note that if I add a1 plus a sub 1, a1 plus n minus 1d, I get a1 plus an. That's kind of obvious, right? a1 plus the explicit formula right here for an. And if I do it with the last pair, well, that's obvious again. That's a1 plus an. But what about with the second pair? Is it clear there that this is going to be the same thing? Well, look at it. You'll have an a1 here, right? And then you'll have an a1 plus n minus 2d plus an additional d. That additional d will combine with the n minus 2d to produce n minus 1d. And thus, every single pair will add to a1 plus a sub n. And there are exactly n pairs because there are exactly n terms in the series. And so I'd have n pairs of the sum a1 plus a sub n. Dividing through by 2, I could say, therefore, a sub n is equal to n over 2 times a1 plus a sub n. This derivation helps me understand how Gauss thought about the problem. It also might give me an alternative formula that perhaps you've seen. Maybe you've seen the formula given as n over 2 times 2a sub 1 plus n minus 1 times d. And if you looked at how you added, say, any particular pair, you see that a sub 1 plus a sub 1 is given the 2a sub 1, and then if you add the coefficients of the d's, you'll get n minus 1d. You'll see the alternative version of the formula pop up right in the derivation. You can use either of those to work out the sum of an arithmetic series. This begs the question, what about geometric series? Is there an efficient formula that can work out very quickly the sum of some geometric series? Let's think about that. So a geometric sum would look like a sub 1 plus a sub 1 times r plus a sub 1 times r squared, and so on, all the way to the nth term, which would be a sub 1 times r to the n minus 1 power. Okay, now writing this in reverse and adding them together like the idea from the last derivation won't work. However, I can exploit the idea that each successive term is a factor of r more than the previous term. And so I can think about what would happen if I multiplied this entire equation that I have written out here by r. On the left-hand side, I'd just get r times s sub n. On the right-hand side, instead of a1, I would have a1r. Instead of a1r, I would have a1r squared. Each of the terms from above are getting multiplied by an r here. Continuing on, I would eventually have an a1 r to the n minus 1. And I would also have an a1 r to the n. And that's because the last term in my series here, if I multiply it by an r, it would give me an a1 r to the n. And what I've done is I've written these in a way that's suggestive of my next step. In the last derivation, we added both sides of the equation together because it gave us a nice result. In this one, we'll subtract these two equations from each other. And you'll see that that gives you a nice result. On the left-hand side, you get S sub n minus R S sub n, just like that. And on the right-hand side, you get a lot of cancellation. A sub 1 will remain, but the A sub 1R will cancel with the A sub 1R in the second row. A sub 1R squared cancels here. Everything inside the dot, dot, dot will also cancel out. And these terms would cancel out as well. And thus, you'd be left with simply a positive A sub 1 and then minus an A sub 1R to the n. And how do you get a convenient, easy to use formula for S sub n out of this? Well, on the left-hand side, you factor out an S sub n, leaving a 1 minus R. You check that with distributive property that works out nicely. Pull out the common factor of S sub n. And on the right-hand side, you pull out the common factor of A sub 1, leaving 1 minus R to the n. Dividing both sides of this equation by 1 minus R, and you have that formula that you were after. A sub 1 times 1 minus R to the n over 1 minus R. And there we have formula for summing the first n terms of a geometric series. And to conclude this video, I just want to do a quick summary of all the different things we learned here and then leave you to do a little bit of practice. So we talked about arithmetic sequences, arithmetic series, geometric sequences, geometric series. You have a whole bunch of problems in the very first problem set to play around with. Start to get the idea, start to get the hang of how these things work. It would be worth consulting the specific examples we came up with in this video, as well as this page of the relevant formulas that you're going to need in order to solve some different things so that you're successful on those problems. Thanks for watching.